All right, let's jump right in. Today, we're going to get our hands dirty with a real landmark paper from 1989 by Alexander Zamolodchikov. Now, why is this paper such a big deal? Well, in a world where most quantum field theories are basically impossible to solve exactly, this work built a stunning bridge. It connects the beautiful, perfectly symmetric, and, most importantly, solvable world of conformal field theory to the much messier, more realistic world of theories with mass. This wasn't just a small step. It was a radical new way to find exact solutions where we thought none existed.
So here's how we're going to break this down. We're going to follow the paper's own beautiful logic. First, we'll set the stage, this tale of two theories, massless versus massive. Then, we'll learn the essential language we need, the language of symmetry in CFT. After that, we'll get to the main event, Zamolodchikov's wild idea to carefully break that perfect symmetry. And finally, we'll see the stunning payoff, a complete, exact solution to a famous physics problem.
Okay, let's dive into this. The whole story really starts at the intersection of two areas of physics that were blowing up at the time, conformal field theories on one side and integrable models on the other.
So you've got these two worlds. On the left, conformal field theory. This is the realm of perfection. It's massless, it's scale invariant, meaning it looks the same no matter how much you zoom in or out. Think of water exactly at its boiling point, that perfect moment of phase transition. It's beautiful, and often it's solvable. Then on the other side, you have massive field theories. This is most of reality. Things have mass, they have a size, a characteristic scale. This is the world away from those perfect critical points, and usually it's way harder to solve. The big question was, are these two worlds completely separate?
And this is where Zamolodchikov's genius comes in. He saw that they weren't separate at all. He realized that you could view some of these complex, massive theories as just deformations of the perfect CFTs. It's like taking a perfect crystal and introducing a very specific, carefully chosen flaw. And here's the kicker. If you do it just right, the new massive theory actually inherits a ton of the beautiful structure from its parent CFT. It keeps an infinite number of hidden symmetries, and that right there is the definition of an integrable and therefore solvable system. So to really understand this bridge he built, we first have to learn the native tongue of conformal field theory. And that language is all about its incredible infinite symmetry, which is all wrapped up in one amazing mathematical structure. And that structure is called the Virasoro algebra. You can't overstate its importance. It is the absolute engine of two-dimensional CFT. If you understand the rules of this algebra, you unlock the whole theory. It's the key to everything that's about to happen in this paper. Now, let's actually look at the math here. This equation defines the whole game. It's telling you how the symmetry generators, these LNs, talk to each other. That first term, the n minus m L the n plus m, that's more or less what you'd expect classically. But the second piece, the one with the letter C, the central charge, that's pure quantum mechanics. It's an anomaly, a central extension that makes the whole thing so incredibly rich. And that little number C becomes a kind of fingerprint for the theory. It tells you exactly what physical system you're describing.
The best way I've found to think about this is to imagine an infinite toolkit. The Virasoro generators, the LNs, are your tools. L0 is like your magnifying glass. It scales the system. L1 and L-1 are like sliders. They just shift things around. And then all the other LNs, they're like these bizarre, exotic tools that warp and twist your system in very precise ways. A CFT is basically a system that's so symmetric it doesn't even notice when you use any of these infinite tools on it. And this table from the paper shows you how you actually use this toolkit to build things. It's brilliant. You start with the most basic thing possible, the vacuum, which is represented by the identity operator, I. Then you start applying your tools. See here, you take L minus 2, you act on the vacuum with it, and boom, you've just created the stress energy tensor, T2, which is the most fundamental field there is. You take L minus 2 and do it again, and you get a higher spin field, T4. The entire zoo of particles and fields in your theory is built up just like this.
Okay, so we've got this perfect, beautiful, symmetric system. And what's Zamolodchikov's radical idea? He decides to break it. But not just smash it with a hammer. He's going to break it in a very precise, very controlled, and very clever way.
This equation right here, this is the recipe. It's the heart of the whole method. You start with the Hamiltonian of your perfect CFT. That's HCFT. Then you add a perturbation. You reach into your theory, you pick out one very specific type of field, a relevant one, phi, and you add it to the mix, controlled by this knob, lambda. This new piece explicitly breaks the scale invariance. It gives the theory a mass scale and kicks it out of that perfect critical point.
And this, of course, leads to the absolute million-dollar question. When you take an infinitely symmetric system and you break it, is everything lost? Do you just end up with an unsolvable mess? Or does some ghost of that beautiful structure manage to survive?
The answer, as Zamolodchikov showed, is that if you're clever about how you break the symmetry, an incredible amount of structure survives. And the way you find it is by hunting for things that are still conserved, what we call integrals of motion. So here's the game plan. You start with your CFT, with all its infinite conserved quantities from the Virasoro algebra. Then, and this is the crucial part, you perturb it with a very special kind of field, a so-called degenerate field. Think of it as a field that has some special properties that constrain the theory. By choosing this special perturbation, you guarantee that even though most of the old symmetries are gone, an infinite subset of them survives, just in a slightly modified form. And any theory with an infinite number of conserved quantities is by definition integrable. It's solvable. You can crack it.
Now, this isn't just some elegant mathematical trick. Zamolodchikov immediately turned around and used this framework to solve a really famous, tough problem in physics, just to show how powerful it was.
He aimed it straight at the 2D Ising model. Now, at its critical temperature, the Ising model is a classic CFT that we understand very well. But the second you turn on a magnetic field, that symmetry is broken, the system gets a mass, and the problem becomes notoriously hard. Zamolodchikov just looked at this and said, wait a minute, that's not a new hard problem, that's just my setup. It's the Ising CFT perturbed by its spin field.
And this is where things get just mind-blowing. Look at equation 1.9. The theory makes a concrete testable prediction. It says that in this system, the ratio of the masses of the two lightest particles, m2 divided by m1, is exactly the golden ratio. I mean, come on, that is absolutely wild. You have a model of magnetism, and out pops one of the most fundamental and famous constants in all of mathematics. It's just staggering.
But he doesn't stop there. It gets even better. The theory doesn't just give you one ratio. As you can see in equation 1.12, it predicts the entire mass spectrum of all 8 particles that emerge in the theory. And these aren't random numbers, they're all precisely fixed by the deep algebraic structure that survives the perturbation, a structure related to the exceptional Lie algebra E8, of all things. This is the ultimate proof. From abstract symmetry principles, you get a complete quantitative description of a real physical system.
And this quote just brings it all home. We're back to the central idea. The ghost of that original conformal symmetry, that infinite dimensional algebraic structure, it haunts the theory. It's still there, even after you've broken the symmetry and moved away from the critical point. And it's this surviving structure that keeps the whole thing solvable and gives us these incredibly beautiful results. So in the end, Zamolodchikov's paper didn't just solve a problem. It launched an entire field, integrable field theory. It taught us that sometimes the most profound physics isn't in perfect symmetry itself, but in the rich, elegant structures that survive its breaking. And it leaves us with this really inspiring question that people are still chasing down today. What other perfect theories are out there, just waiting for the right kind of push to reveal all their hidden secrets?